video. This semester, we took an Intro to CFD class at Lamar University. So stay a while and join us on our journey for analyzing turbulence, drag, pressure, and pressure analysis. Our objectives for this video are the following. First, we're going to visualize turbulence to identify possible efficiency impacts. Second, we're going to analyze pressure, which impacts the lift, steering, and the propeller performance. Third, we're going to create an accurate analysis of drag to assist in runtime and top speed calculations.
So the first CFD animation test confirmed that there is turbulence in the rear. Based on the insights, the pressure contours showed that the higher pressure at the stern of the ship, which is what produces the lift and causes the boat to plane at the high speeds. And furthermore, comparing velocity vectors and the pressure contours, when the fluid speeds up to go around the boat, there can be a huge drop in pressure.
So, after we did our preliminary simulations that we just showed, we moved on to doing more complex simulations now that we've actually developed a skill with the software. The first one we did was here with a top view of our boat. This view is developed by finding the waterline of our boat and then importing that profile as a geometry file into ANSYS, and then using that for our simulations. As you can see at the top here with this mainly blue picture, this is the turbulent kinetic energy. Whenever we impart a lot of energy into water, that means we're losing efficiency. Thus, we have to be aware that if we can reduce the amount of turbulence we produce behind our boat, that will increase our efficiency. Furthermore, we can see here in this second picture that we can see that the pressure is higher in the front. This helps produce lift for the boat. For the third picture, we can see that there are vectors of velocity going around the boat, and in the back you can see how they curl back and form a vortice. Finally, we have our animation picture here from the top, and it actually depicts something called Kármán vortices, where we can see it causes like a wiggle behind the boat as the flow begins to develop. Furthermore, we also want to do simulations of the side profile to compare with the top view. We used a similar method of importing the geometry, and we did similar tests. And once again, we were able to confirm. If you look at this yellowish greenish picture here, it has red under it at the front, which means there's high pressure there. High pressure would develop a force under the boat that helps lift the boat up, similar to how airplanes can generate lift in the same way. And furthermore, once again, we can see in this bottom right-hand picture here, vectors of the velocity of the fluid as it flows around the boat. Then we moved on to a slightly more complicated simulation, which is a 2D multi-phase CFD. Once again, we take the boat, but this time not just the water line, but the whole boat. We import that geometry, take a profile, mesh it, which is creating a mesh for the simulation to run off of. Each mesh has made up or is comprised of many cells. And essentially, the computer calculates what's going on in each of those cells. Thus, more cells means it takes more time because the computer has to do more calculations. The multi-phase here means that we have two different fluids. One of them is air, and then one of them is water. The air is depicted in red, and the water is depicted in blue. This allows us to see how the two interact as our boat moves. So, if our boat is still, you will see something like this bottom left-hand picture, where it's just a flat line, and the air is resting on top of the water. But as we begin to move, not only does water bunch up in front of the boat, but as it flows from under the boat and out behind the boat, a wave is generated. You can see that in our simulation in this bottom right-hand picture. This is useful because it also helps us in finding out what is the wetted area of the boat, because it'll help us trace a water line and how that affects our boat And the more of the wetted area that touches the water, the more drag that we will experience. So then, we also try to do this in 3D, but this vastly complicates the process because now instead of it being two-dimensional, it's three-dimensional. There's much more problem solving, and the mesh is more important. You see, if the mesh is improperly made, the computer will throw errors. We were able to fix a lot of these errors and get some simulation to run, but it ran with this odd error. As you can see, it almost looks like there's a small explosion of the water below in the back of our boat. It can be theorized that possibly what happened is that with how the simulation is set up, there is some water that is inside the boat, and whenever it interacts with the boat geometry, and then the other fluids on the outside of the boat, and the fluids on the inside of the boat, there is some kind of reaction that causes the simulation to come out erroneous like this. In the future, we would love to fix our geometry, but that requires us to completely change how we have modeled our boat. Thus, we've settled on this as of right now. Finally, we move on to our 3D boat CFD to get our drag analysis. Once again, we import our boat geometry, create a mesh, import that into a setup where we determine different types of variables and formulations that we'll use. For this one, we use something called a viscous model with the K epsilon setup, which is a two-equation setup. And then after running this simulation, we're able to go to our results and go to the function calculator. Here, we're able to choose that we want to see the forces on the boat and even pick a specific direction. With this, we were able to find that the force on the boat, the drag force, as simulated by the computer, is 112 newtons. This comes out to roughly 25 pounds of force. Our expectation was that our force would probably be around 30 newtons of force, or pounds of force. But likely, because of the inaccuracies in the simulation, the quality of the mesh, and the materials that we've chosen, there were some losses to accuracy. But because this is relatively close, we can consider this evidence as supporting our motor selection in the future, which is why we need to know the drag force in the first place.
So, the CFD results were very useful for us, but of course there were some flaws. The first one is that the boat was simulated without the extra weight added onto it. So velocity, pressure, and other aerodynamic factors were calculated based on the boat's operations without the solar panels and the other equipment that we were planning to put onto it. With the extra weight on the boat, there will be unforeseen circumstances, such as certain instances of capsizing. We hope to simulate the boat with the added weight to calculate its aerodynamics and hydrodynamics with the extra weight in the near future. And there were also different circumstances added to the simulation, so there were different velocities and different pressures and other dynamics that were animated as a result. But despite all the flaws, the simulations allowed a better understanding of how we want the boat to behave, and by making the necessary changes, the boat will be more efficient for when we build and operate it for the competition.
Thanks for watching!